Okay, so let's start. We were discussing uh, the proof of Thevenin's theorem. Then we were discussing one of one of the applications, and the applications was from the perspective of building a voltage regulator. We obviously won't be building a voltage regulator right away because one way of looking at this course essentially is to build a voltage regulator. But I wanted to motivate you as to why these concepts are necessary and why uh, some of the effects that we are going to discuss today, the next class, and probably in the next few weeks will be the foundation. We lay the foundation of what's going to come, right? So one of the things that I probably didn't mention enough in the first two introductory classes where I was trying to motivate you was the fact that uh, the maths in this course is pedestrian. It is at best maybe at the level of class 11 or 12, right? But the stuff that is required is to relate multiple concepts together as one progresses. And it's probably not that intuitive to appreciate it at this point. The only example that I can give you, or only anecdote that I can give you, is not as if when quiz ends, the learning for that week ends. It's essentially the learning for that week begins, because we will see that in lecture 25, we'll be referring to something that has been taught in lecture 3. Right. So when you pick up the concepts, keep that in the back of the mind, that it's not just the exam is over, get my mind cleaned of it, right? So you'll have problems doing that during the midterm and the inserts. So I am saying this upfront without having any information about you guys, because I don't want to bias myself with respect to what you might think or might not think, right? So this is what I have observed over the years. So I just wanted to make it clear. Okay. So the stuff that we were discussing in the last class was this. So let's say we have a fixed battery of value 2 volt, and we wanted to get 1 volt out of it. And the obvious thing to do was to use a voltage divider. We chose some resistances, let's say 1 kilo ohm, 1 kilo ohm. Then we said that if we connect something to this port with we took the example of a cell phone, and let's say this is RL. The RL models the amount of current that we are drawing, and RL obviously will be time dependent, because the activities that we do with our devices are also time dependent, right? So this is a time dependent variable resistor effectively, which essentially means that amount of current that you are drawing out will also vary with time. If that happens, then naturally this voltage V naught will also vary with time. So one of the purposes of voltage regulator is to ensure that the voltage gets steady, right? It doesn't fluctuate with whatever happens. Even if, for example, this 2 volt supply also fluctuates because of some fluctuate in the power supply or something else, the expectation is this V naught will not change, right? As a consumer of electronic goods, that is our expectation, because if it changes, then many of the other properties of the stuff inside the network might change. So this is what is required. And let's assume this 2 volt supply right now is constant. Let's not overcomplicate stuff. And then what we said, that one way to understand the requirement is to Thevenize the circuit on the left, right? Thevenize this part, right? So that would help us to understand what will be the effective requirement of the block that we are trying to design. So Thevenin equivalent of that part essentially becomes, so essentially, when we are trying to Thevenize something, we are, when I put a box and say that Thevenize it, it essentially means that outside, whatever is outside the box is irrelevant. We have to remove that. So in this case, the RL is not necessary. So the Thevenin equivalent of that becomes 1 volt, and this becomes 1K parallel 1K, that is 500 ohm. This becomes the box, and you have RL here. And then we further said that, let's say this RL varies between 100 ohm to, let's say, 1 mega ohm. Then all of you rightly pointed out that the issue will be with this 100 ohm stuff, simply because if you have 100 ohm, you have a lot of current which will drop across the 500 ohm resistor, right? And our output will output across RL will fluctuate meaningfully from 1 volt, right? So this is where we were. And then we said that if we have to fix this issue, what needs to be done? Now, when I say what needs to be done, you have to understand that we are talking from the context of a designer, not the user. User is giving you the RL, right? You as a designer, we are in the job of building the stuff inside the box, right? So from as a designer, since we are in charge of building the stuff within the box, which means that we have to do something inside the box so that I can still drive RL. It's not as if I can change RL. So then the suggestion, a very good suggestion came, was to ensure that this resistance 500 ohm is too much. So naturally, we have to reduce it. We have to reduce it much lower than 100 ohm, because it is only when we reduce it much lower than 100 ohm, we'll have the output will be closer to 1 volt or approximately equal to 1 volt, regardless of the range of RL, right? So that is also good. So now the next step that we took was to say that, so let's say we want this 500 ohm resistance to go to, I don't know, maybe 1 ohm, right? So if that has to be equivalent resistance, or Thevenin equivalent resistance has to be 1 ohm, then naturally these have to be 2 ohms, 2 ohms, right? So so if this is 2 ohms, then we saw that even when you are not driving anything, even when in the absence of RL, you are drawing 2 volt by 4 ohms, that is 500 milliamps of current, 0.5 amps of current. Use a different color. You are drawing 0.5 amps of current, even when your device is essentially off. Okay, so your typical cell phone battery is 1800 mAh. Let's say you round it off to 2000 mAh, that is 2 ampere hour. So essentially, this is telling you that even when you are not doing anything, your cell phone will get drained off in a couple of hours, right? So naturally, the power management circuit inside your cell phone cannot be this, right? So it has to be something which, in plain English, it has to be something which does not draw a lot of current when there is no activity, but draws only sufficient amount of current that is required for the activity, right? Does that make sense? So when you are watching, let's say, a video, or in a cell phone call or a video call or something, then there is a lot of activity, right? That needs to be powered. At that time, you supply whatever current that is necessary without affecting the voltage. But when the phone is in probably shut off or aeroplane mode, or you're sleeping or something, then there is no activity. Then you don't want to draw a lot of current. And that statement should be true with respect to the amount of fixed current that you are drawing. Because when I say fixed current, what I essentially mean is that the stuff inside the box is only there to drive RL, right? So any current that is not going to RL is a waste. Do you agree? So any current that is not going into RL is a waste. So we would like to minimize the waste, right? We'd like to minimize the waste everywhere in every section of our life. So we also like to minimize the current that is getting wasted. But if we just simply put our circuit up like this, then naturally you can see that there is a lot of wastage that is happening, because even when RL is supposed to take up zero current, for example, I mean, if it's 1 mega ohm, it's almost few microamps of current that can go in. But still, the stack that you have built right now will be taking half an amp of current all the time. So that's not a wastage, right? So this you cannot do. So in philosophically, what are we looking at? Philosophically, what we are looking at is a way to, so let me rephrase the statement that I made 2 minutes back. What we want to do is to ensure that the wastage of the current is minimal, which under the condition that RL varies from, let's say, 100 ohm to 1 mega ohm. So, which essentially means that when RL, let's say, is 1 mega ohm, we would like to also waste minimum current. But when RL equal to 1 mega ohm, the amount of current that will require to sustain 1 volt will be what? So let's say I have RL of 1 mega ohm. I want to sustain 1 volt across it. How much current should RL see? 1 microamps, right? So essentially, when RL is 1 mega ohm, the stuff inside the box should provide 1 microamps. When RL is equal to 100 ohms and I still want to sustain 1 volt, approximately 1 volt, how much current am I expecting? 10 milliamps, right? So your box has to be aware of the requirement of RL, right? So it's not as if it's an open loop design. You can just fix it and connect an RL and things are going to work. There has to be some way of sensing the load and feeding that information back into the box, right? So that it understands when should I supply 1 microamp, or when should I supply 10 milliamps, or when should I supply 1 milliamps, right? It's almost as if somebody is sitting at the outside and giving you the information of, hey, now I need to supply more, or now I need to supply less current. So this electronically, this can be done using feedback, right? This is one of the reasons you need feedback, right? Feedback has like n number of applications, but this is one of the applications where you can use the concepts of feedback to ensure that your power efficiency becomes better. When I say power efficiency, what I essentially mean that your wastage of current minimizes. Okay, right? So again, these are very heuristic concepts that I am throwing at you right now. We'll get into these in more detail when we get into feedback. But still, I'm trying to give you an idea of why we will be doing what we will be doing in the days and the weeks to come. Okay. Okay. So let's park negative feedback for few classes. So let's get back to the effect of loading, right? So yes. Right.
Then we can see that there is no current anywhere.
Correct.
But when we disconnect RL from here, you can see that there is an internal
Correct.
current.
Yes.
So I'm just questioning how.
Great question. So his question is, in case if you couldn't hear, his question is, if these two circuits are supposed to be equivalent, then it looks like if I disconnect RL from the right-hand side, there is no current through that 1 volt through this loop. But if I disconnect RL from this part, then still I see there is a power consumption in the circuit, right? So if these two circuits are supposed to be equivalent, then where is the fallacy?
Equivalent is only meant when the load resistor is correct.
Okay, that statement is correct, but how that is related to this question? Correct. Excellent, right? So Thevenin equivalent only says that the external behavior is same, right? So whatever you are observing at the port doesn't change. It doesn't make any statement of whatever is stuff inside the box will be identical or not, right? It's a model stuff. When you are modeling anything, you are modeling for one particular or two particular things. That is again a very generic concept, right? When you are modeling something, you are modeling for that particular behavior. You are not modeling for anything else in the circuit, right? In this case, it's not modeling for the amount of power consumption. It's only modeling for the output voltage and output current, right? So it might be same, might not be same. That totally depends on the particular type of circuit, because Thevenin theorem doesn't model for same, to keep the power consumption same between the equivalents. But very good question. Thank you. Okay. So now, I hope some of you have taken a look at the tutorial questions. So one of the questions that we had there was, why is it flicking? Okay, so one of the questions was, there is a box and you connect something, and then you figure out whether it's a voltage source, current source, or a mix and match of both. So let me give you an idea of what we are trying to drive home through that question. So let's say I have the same question. So let's say I have a box. What's happening here? So let's say I have a box, and I observe that the stuff inside the, I observe that if I'm not touching anything also, right? Should I restart? Okay, so maybe I can restart it once.